So now we will be discussing about as you already know that there are two kinds of representations of a signal. So one is time domain representation, another one is the frequency domain representation. So that means in the time domain, how the signal is changing with respect to time domain. We will plot how the signal is changing with respect to time. Let us consider, so that is, let us consider this is time axis, and we will be representing how the signal is changing with respect to time. So this is nothing but the time domain. And another way of representation of the signals is frequency domain. Is the frequency domain, and in this we will be having the x-axis as omega. So the omega, that means the frequency domain, and we will represent what are the signals. Let us consider. So this is x of omega, and we will be having, so what frequency has got some magnitude. So what is the, and this is a frequency, and this is a magnitude of that frequency component. Okay, not magnitude, and then this is a frequency, this is amplitude. Let us consider this is modulus of x of omega. This is a magnitude of this frequency component, and this is a magnitude of this frequency component. That means we will be representing what are the frequency components present inside the time domain signal. Let us consider this is the time domain representation, and this is a frequency domain representation. Okay, there are two kinds of representations of any signal. That is, one is time domain where the x-axis is time, another one is frequency domain where the x-axis is the frequency axis. Okay, now let us move on to the systems point of view. Okay, so let us consider a system, as you already familiar with the systems, and this is an LTI system. It is satisfying both linearity and time invariant property, and I am giving the input as x of t, and I am getting the output as y of t, and the impulse response of the system, when the input is impulse signal, I am going to get some output that is nothing but h of t. So what is the relationship between these three? So y of t is equals to x of t convolved with h of t. Y of t is equals to x of t convolved with h of t. This is a relationship between the input, output, and the impulse response. Now taking Fourier transform on both sides. Taking the Fourier transformer on both sides. As you already familiar with the Fourier transforms and their properties, and you already familiar with the properties. And by taking the Fourier transform, and this becomes y of omega. So y of t, the Fourier transform of y of t is y of omega. So that is equals to, and using the property. So what property? So using convolution property. Using convolution property of Fourier transforms. So x of t convolved with h of t becomes multiplication in the frequency domain. If you don't know the property, please go through and refer the convolution property of the Fourier transforms, as that is x of omega, the frequency domain representation of x of t multiplied with the h of omega. And you can easily understand this h of t's frequency domain representation is h of omega, then x of t's frequency domain representation is x of omega. From this we can write the h of omega is equals to y of omega by x of omega, and this is nothing but called as transfer function. Remember students, this is called transfer function. We can also call this as, or we can also call this as system function, transfer function or system function. Okay, h of omega is equals to y of omega by x of omega. And you can easily understand the relationship between the h of t and transfer function. So let me write here. So the impulse response h of t is equals to the inverse Fourier transform of h of omega. Conversely, we can also write the system function, that is h of omega is equals to the Fourier transform of h of t. So this is a very important relation between the transfer function and the impulse response. They are related like this. And this is when the frequency domain, we use that as a Fourier transform. Okay, so the same thing, the same concept can also be extended in another frequency domain, which is called as S domain. S domain is also a frequency domain, that is also known as Laplace domain. Okay, so let me go with the Laplace transform. Everything is same, and except let me clear this. Okay, if you have note down, so let me go with the Laplace domain, that is Laplace transform, taking Laplace transform on both sides. If you take the Laplace transform on both sides, so y of t becomes y of s. Y of t becomes y of s, that is equals to x of s using convolution property of Laplace transform, x of s multiplied with the h of s, using convolution property, Laplace transforms, y of s is equals to x of s multiplied with the h of s. Remember, students, so this convolution becomes multiplication in the Laplace domain as well. Okay, if you take the Fourier transform or the Laplace transform, the convolution becomes multiplication in the frequency domain. And from this, we can also write this h of s is equals to y of s by x of s, and this h of s is called as, again, this is transfer function, or system function. We can call this as system function, transfer function or system function. And let us come to the relationship between the transfer function and the impulse response. Let us consider, and we can write h of s is equals to, okay, Laplace transform of h of t, or h of t is equals to inverse Laplace transform of, we can also write this capital L inverse is nothing but inverse Laplace transform, or we can also write here simple L here, capital L here. So h of S domain or the frequency domain, one another same, where S is a complex frequency, that is the S domain. That's the relationship between the transfer function and the impulse response. Okay, so thank you, and we will be discussing more in the next coming lectures.